Hi, everyone. So this is have no fear, and that is the opposite feeling that I'm feeling right now. And it's just the math you need to know for monitoring. So in monitoring, we have these mathematical concepts. When we're visualizing the data, we may be using log scale, for example. So we're going to look at that. We also have a ton of data, and we want to summarize it. Typically, we use the center, like median, mean, mode, spread of the data, and we may also be looking at percentiles using relative standing. So we're going to be looking at those things, so if you're interested, stick around. The very first thing is logarithms, and obviously for that, we're going to use XKCD. So this is the XKCD on height, and this XKCD contains the entire contents of the universe. I know it looks tiny up there, but that's what it contains. The objects and the sizes of those objects, they are not to scale, but what's to scale here is the height of where those objects are placed. And this is accurate on a log scale. So first of all, we're going to start at the top of the observable universe, and that is hanging up on top of your heads for 46 billion light years up there. That is 435 yottameters, which is 435 times 10 to the 24 meters. And by the way, I just want to make a note that there's a cat that is being dropped from the top, and we just want to see if it's going to land on its feet. I'm going to root for the cat, and I think it's going to land on its feet. So this is the height that we're covering in this log scale. It is a ginormous height. It is the biggest height you can cover, and that is the point of log scale. So we want to display a very wide range of values in a compact way. We're going to go down to the grass on Earth, which is what we have on the stage, so very convenient. We are going to look at the Great Pyramid and how it's shown in a log scale. We're also going to look at the Eiffel Tower. So the Great Pyramid in a linear scale is obviously a pyramid. But in a log scale, what happens is from top to bottom, as you go down to the bottom of the log scale, on the y-axis, what's going to happen is those values are going to get stretched up. So what ends up happening to the Great Pyramid, that it looks like a bullet instead of a pyramid at the bottom. And if you think about it, on the log scale, you have powers of 10 on the y-axis, right? You have 1 to 10, 10 to 100, 100 to 1,000. So you're covering less and less values towards the bottom. That's why you have more room to stretch them up like that. The Eiffel Tower, on its sides, it's inwardly curved, and that approximates an exponential curve. So on a log scale, it's correctly drawn in this comic. Exponential curves are represented as straight lines, so that's what happens to Eiffel Tower's sides. Next, we're going to look at the different heights here. So 1 light year, it is an order of magnitude 10 to the 15 meters. 1,000 light years is at 10 to the 18 meters. Million light years, 10 to the 21, and billion light years is 10 to the 24. So the distances in between is actually a multiplication by 1,000. And that is the point that in log scale, instead of adding the same quantity to get to the next level, we are multiplying by the same quantity. As I'm speaking, your ears are perceiving the sound at a log scale. And this is so your ears don't explode, because you need to be able to hear whisper, mouse squeaking, but also you need to be able to hear jet engines flying. So it's a very wide range that your ear needs to accommodate for, and that is why normal conversation that you may be having in a hallway that is at 60 decibel, and its vacuum cleaner is at 70 decibels, so the difference in between is perceived by your ear as 2 times as loud. And Gustav is the gnome who came up with that. Now, in monitoring, we may have disk usage or memory usage type of data series like this. And as you can see on top, we see the used data series that is clearly visible. And then the free and cache usage is not very visible, is actually delegated to the bottom pixels in this graph. When we redraw this in a log scale, and this is using log base 32, it actually has room to grow. Just like the Great Pyramid, it got stretched. So you can actually see the free and used data series down there. I want to talk a little bit about origins of logarithm, because I didn't know about this and I think it's phenomenal. So in late 16th century, folks didn't have Gen AI and ChatGPT. So they just had to make do with observational astronomy and celestial navigation of ships as the top scientific fields that they work on. And these fields required large multiplications of large numbers, and mathematicians had to help speed up these large multiplications of large numbers. So what ends up happening for mathematicians is that their lives were miserable because they had to do tedious calculations. These calculations were error-prone, and they suffered. They couldn't go to the pub and tell physicists that math is better than physics. So John Napier came up with logarithms, and this was in early 1600s. And he called it the wonderful laws of logarithms. And what logarithms do for us is that they turn multiplications into additions. So instead of multiplying ginormous numbers, we are going to be adding ginormous numbers, which is an easier problem to solve. And they also turn divisions into subtractions. And you can do all this with the help of a log table at the time. So this is early 1600s. Henry Briggs came up with the common logarithm, which is log base 10 log table. Of course, today we use computers for that. Now, I'm going to move on to another reason why we may be using logarithmic scale, and that is to display relative change instead of absolute quantity of change. And I think we understand this best when we talk about losing money. So if you bought stock at $20, and if you lost $10, that is a 50% loss. But if you bought stock at $100 and you lost $10, that is a 10% loss. So it doesn't really matter that you lost $10. What matters is the relative quantity or proportion of what you lost. So this talk came with a time machine that wasn't, in the program, wasn't told to you, but we're going to take that time machine and we're going to go back to 1930 October. And we're going to take a look at the Dow Industrial Average at the time. As you can see, it's within the hundreds in value. And in 1929 October, you are seeing a dip. So this dip is what's marking the beginning of Great Depression, and it is called the Wall Street crash. We're going to take that time machine and we're going to actually go to 2021, and we're going to now visualize 100 years worth of the Dow. As you can see now, the Dow is actually going into the 30,000s range, and the dip that we saw just a little earlier now looks like a happy little bump. Now, we know that our graph is not telling us the real picture, and Dorothea Lange will tell you so. She was the very first documentary photographer before that term was coined. And Dorothea documented images of migrant workers who were moving to California in the hopes of finding work to feed their families. And this is the image, the photo of Florence Owen Thompson. And in addition to the two children next to her, she's actually holding a baby, which is something I didn't notice until very recently. So our graph is actually hiding this real picture from us. So how can we get back this important information? On the left side, we have the linear scale graph. On the right side, we have the log scale graph. And as you can see, obviously, in the log scale graph, the y-axis is going as the powers of 10, as we expect. So in the linear scale graph, we have the values between 0 and 10,000 on the left-hand side. And on the log scale graph, we have more room to fit those values. So they're actually going to look stretched up like the Great Pyramid. And that means we can see the rates of change clearly. So the Great Depression, the beginning of it, is actually back to us, even though we're now visualizing 100 years worth of data. And we can also see the 2007-8 financial crisis, which some of us had to live through. Now, the final one that I'm going to go over for log scale is it's easier to identify exponential growth in a logarithmic scale. So for that, we're going to look at the confirmed COVID-19 cases from the beginning of the pandemic is what I want to focus on. And in the beginning of the pandemic, we were asking questions like how quickly this thing is spreading, what's the infection rate? Because we wanted to make decisions based on that, like are we going to be going to a lockdown mode? Are we going to be working from home forever? For introverts, working from home forever is not a bad thing. speaking from experience. In log scale, though, so in linear scale, you couldn't really tell if that was an exponential growth. And in log scale, you can see the spike, but I really wanted to see the exponential curve, so I basically plotted it. For the first 2 weeks of data of confirmed COVID cases, actually in linear scale, you see the exponential curve, and on logarithmic scale, you see the straight line, so it looks like a beautiful exponential growth that is clearly visible in log scale. And this is a latency graph that is in logarithmic scale from the SRE book. And it is actually displaying data over a very wide range of values. So it is going from 10 to the negative 3 seconds, so that's like 1 millisecond all the way to 100 seconds. And you can clearly see the rates of change here. Now we're going to shift gears and look at how do we describe the data. And one of the very first things that we look at when describing the data is to look at the center of data. And for that, I think all of us know how to take an average, so this is pretty primal. But one of the things that we think about when taking the average, and an analogy for an average is that it is the balance point by the weight of the data points. So if you had norms and you put them on a seesaw, you wanted to balance that seesaw based on the weight of those norms. And these norms, they don't just play, but they also work. So they have salaries. So we're going to take the average of their salaries. So 400,000 over 4, which is the count of the norms, and that is the mean at 100,000 right now. Next, these norms are going to make friends with the world's richest norm, who ends up, who is also swimming in gold. So what ends up happening now, if you add this data to the sum, earlier sum, and divide it by the new count, then you get this 1.4 billion as the mean. So the 4 norms, with the humble salaries now are represented by this new mean, which is 1.4 billion. The norms are not happy because this is not a good representation of the average norm's salary. And if you start looking into this area in statistics, there's this very famous quote that comes up again and again. And it goes like this. Then there is the man who drowned crossing a stream with an average depth of 6 inches. And I can guarantee you this man was not a norm. So averages hide the outliers, and outliers skew averages. So averages are not enough to describe the center of the data. So we need something more. So we're going to look at the median. And median, we can think of it as balancing on the seesaw by the number of data points on each side. So first, we have to sort the data. And after we sort the data, you can see the outlier is now going to be where it should be, which is on the edges. Then we chop the data in the middle with a guillotine, and that is going to be the median. Now, if we have even number of data, then we can just average out the middle 2 points. NFL players' salaries is a good example of this. In the newspapers, we typically see of the mean, the average salary, which is 2 million. This is old data from 2018. But this mean is heavily skewed by awesome quarterback salaries like Patrick Mahomes. The median salary, on the other hand, is more representative of the average player's salary. So that's 860,000, and that is more like, for example, a kicker's salary. So when you're negotiating your salaries, don't just look at the average, but also look at the median. And mode, so mode is the value that appears the most often in a data set. It can happen that there's multiple modes. It can happen that there's no mode. There is really good blog post by Brendan Gregg on multimodal data. I would recommend that you take a look at that, but I'm not going to go into too detail into mode here. So this is from the Elasticsearch blog, and let's say that you have a public-facing website and you want to make sure that your norm visitors are having a good response time. So one of the initial statistics that you may look for is the mean and median latency for that. And here, the red and blue lines are the mean and median latency plots, and they are hovering around 50 milliseconds, sometimes peaking at 75. So things are looking pretty happy, rosy in median level, but that's not enough. We are going to be looking at percentiles as well. So that is, the green line is the percentile line. This is from Grafana blog post, and it is talking about over-provisioning versus under-provisioning your Kubernetes resources and correlating the average CPU usage to max usage to understand that. If you're over-provisioning, then you're paying way too much, more than you need. And if you're under-provisioning, then you may have performance degradation. So to be able to basically ensure that you're not over-provisioning or under-provisioning, then you can use this type of graphs where you're correlating average to max CPU usage, for example. Another thing that we care about is the spread in data and how do we measure that. So for this, the analogy is thinking about your data, and if you were to hold all your data points in your hands, would they be concentrated in one spot like a golf ball, or would they be dispersed all over the place like a ginormous cotton candy balancing on top of, a human's head in a fair? So for measuring the spread, there are different ways to do it. If you were to do the max minus min, meaning using range, that means that you're being affected by the outliers. Another way to do it is using interquartile range, which means that you're taking the middle 50 of your data. It's like taking the heart of the data. This is not going to be affected by the outliers. And another way is using standard deviation, so I'm going to look into that. Now, all of you in the room, you are a shoe manufacturer. And I am going to give you just one data point. The average adult female shoe size is 8.5. So that data alone is not going to help you to be able to decide how many shoes of each size to produce. So for that, you needed to know the distribution. And that is how standard deviation helps us. It helps us in understanding how concentrated the values, the data points are around the mean. Now, this is the empirical rule, and Carl is the norm who came up with it. For a normal distribution, basically there are certain properties that we can assume. 68% of our data points are mounted up on top of the bell curve. Over there, one standard deviation away from the mean. 95% of our data is 2 standard deviations away from the mean, and if we go out by another standard deviation, at 3 standard deviations away from the mean is 99.7% of our data. Now that's all good. Unfortunately, we cannot really use that for monitoring, but we're going to get into that in 1 second. So what kind of data does this apply to? The empirical rule typically applies to the real world data, and that is, for example, age of Nobel Prize winners. And when I look at this graph, I'm hopeful. Other examples are baby weights. If any of you had babies, then you may know about this. Basically, when humans produce babies, they have the distribution of like 1 million babies' weights for the statistical category, and then they look at it, and they look at the baby's weight, and then they decide whether the baby is in a healthy percentile with respect to 1 million babies who were produced from the same category. Or height data, for example. So in monitoring, like we said, we typically have skewed distributions. And as the distributions are skewed, we really want to care for the long tails, for example, of latency. And how do we measure that? Like, how do we understand better the long tail in latency? So one of the ways to measure that is to look at relative standing of things. And we understand best relative standing. I think we understood this when we were taking exams. So if you took an exam and the mean was really, really low because it was a really, really hard exam, it didn't matter that you scored low. What mattered is how well you scored with respect to everyone else. And same thing with an easy exam with a high mean. I really like this analogy for percentiles. It says in a race of 100 people, P99 is the time for the 99th person to cross the finish line. And this is my half marathon percentile. So what is kth percentile? It is actually the observation value or the data point that divides the data into two sections, two parts. The lower part of the data represents the kth percent of the data that is below this value, and upper part of the data is 100 minus k percent of the data points. So in this case, this would be a physics test score for a norm. That would be the kth percentile. Quantile is just a generic term that covers more, right? So quantile is the cut point when you chop off your data, and in the case of if you chop your data into two parts, two equal subparts, that is a two quantile, also known as a median, also known as a P50. And 100 quantiles is when you have a lot of patients and you chop your data into 100 pieces of equal subparts, and that is called a percentile. Phi quantile is a term that I see in Prometheus, and it is basically the number that is ranked at phi times n across n data points. So we seem to like to refer to things in different ways. So we're going to look at an example. How do we calculate percentiles? And this is a very naive implementation to find P90. We have 13 data points of exam scores. So what we're going to do is, since we want to find P90, we're going to say 0.9, which is 90 over 100, times 13. And then we're going to round that number up to 12. So it is the 12th data point here. 77 is P90 or 0.9 quantile. And 90% of the scores are less than 77 here. And 10% of the scores are higher than 77. So in US, the Census Bureau actually publishes the household income dispersion. So you know your own income, and you now know everybody else within the US, what percentile and what income maps to that percentile. So now you can identify which percentile you're in across all of the United States. Another thing that US Census Bureau does, in addition, is to measure the income inequality based on the highest percentile and the lowest percentile, and that is called the Gini index, and that has been increasing lately, so that's not a good thing. One thing about percentiles is that they have universal interpretation. So it doesn't matter what type of data we have. We could be having salary data, weight data, latency data, or non-physics test scores data. 95th percentile always means that same thing, which is the value that ranks at the location of the data where 95% of the data points are below it and 5% of the data points are above it. And it doesn't mean the mean or the standard deviation of these data points. It doesn't matter, sorry. It doesn't matter what the mean or standard deviation for the data points are. So this is an example from the Google SRE book that is showing P50, P85, P95, P99 latencies. And on the y-axis, it is logarithmic because it is covering a wide range of values from 1 millisecond up to 10 seconds. So what it's saying to us is that typically the requests are taking 50 milliseconds, which is pretty good. But it is also telling us that 5% of those requests are going to be 20 times slower. So P95 is at 1 second here. And it is even telling us further that 1% of our requests is even slower than that. So it's at 5 seconds. So we really do want to care about those higher order percentiles and observe them and optimize them. Because in a distributed system, even 1% of the requests could have effects in the downstream, clients. Now, how do we calculate percentiles in the real world? So what we typically have in the real world is that we have billions and billions of values, especially when we're monitoring. If you have services that are generating maybe 1 million requests over 1 million requests per second, for example, and if you need to find the P50 over a 24-hour period, then if you do the math, you end up with 86 billion values that you would need to sort, first of all, store, sort, and then find the middle point. So that's a lot of values, and that doesn't scale. So what we need to do is we need to approximate it. And to approximate percentiles, we actually have existing compressed data structures that we can use. And these are things like T-Digest, which has a beautiful paper by Ted Dunning that I urge you, it's really easy to read. It is made really accessible to all of us. I think it's awesome. Greenwald, Kana, HDR histogram are a few of the other ones. So there's quite a few of different ways to do this. But what all of these things do is they read in stream of data points, and they approximate at any given time the kth percentile value for that streaming data. So these are my key takeaways for you today. Log scale graphs work to show the contents of the entire universe. So if you need to show a wide range of values in a compact way, then they're good for you. It's good to observe the long tail of your latency with high order percentiles. And the last two are about statistical potholes not to fall into, which is averages, they get skewed by outliers, and percentiles that we use in monitoring are most of the time approximated, so we have to be careful about what we do statistically with them. And with that, I'll end it. Thank you.